And guess what? We're not done with current sense. I seem to be a little obsessed with sensing current, but this is the ACS 712 chip, and it's a Hall effect based linear current sensor IC. And so it uses the Hall effect. It does not use a resistor to go in and then drop a voltage across it, but the current actually goes into the chip, into a couple of pins, and then out another couple of pins. And it has a Hall effect sensor that senses the magnetic field created by the current going through the pathway that goes through the chip. And then based upon that Hall effect, or based upon that magnetic field, it gets a current level off of it. And it's really ingenious, so you don't interfere with the current at all, or the current, your primary current going through. I believe it's got, let's see, it says here, it's a 1.2 milliohm internal conductor resistance, so milliohms. So you're talking about 1.2 thousandths of an ohm. And what we were using on the 4080 was a 1 ohm resistor, which will have some effect on overall on your circuit. It has to be considered at some level when you use anything like a 1 ohm or a 10 ohm or something like that, a tenth of an ohm. But this is a 1.2 milliohm. Plus, you can put a lot more current through something like a 1.2 milliohm because it's going to generate much less heat because of your IR heat relationship. And it's a 5-volt single supply operation. It's also an SMD package, but it has been already pre-packaged in this nice little, you can see that into the shadows there. It has been pre-mounted on this breakout board, and there's a chip, of course, some resistors, might be a cap, because I know there's a filter cap in the data sheet when I read through the data sheet. But your current goes in here, in and then out, and then you have your VCC and ground for the chip itself, and then you have an out. Sorry, you have your VCC and ground here, and then you have an out that's your voltage out, which is representative of the current, and your current goes in here and out here. Isn't that neat? So they just packaged it up where you could easily play with it. And let's see, motor control, load detection, management, switch mode power supplies, you know, all the typical overcurrent fault protection. It's not intended for automotive applications. I wonder if that's because of all the, well, it's just not rated for automotive. That requires a special rating to get that. Now here's what is implemented in this device here. This is the circuit implemented. As you can see, you've got your current that's going to come through here, down through here, and that internally there you'll have a Hall effect sensor which will sense the magnetic field through that path, that's going through that path. And I believe the filter is for low frequency filter. The data sheet said to put this in if you're going to use a low frequency. It's a low frequency filter to help for noise reduction. And then of course you're doing a little bypass cap on your 5 volts there, which that's on that circuit. That's already on that board, so that'll be convenient. And then V out. So that's what we're going to do. We're going to run some current through there, and we're going to see what kind of performance we get out of it. Now this is the chart I wanted you to see. I just went through a dozen charts there looking at them, but probably the most the one everybody would want to see would be the output voltage versus the sensed current. And you know, what kind of voltage can we expect on the output versus when we put current in. And it doesn't seem all that sensitive actually when you look at it. you know, we were dealing with 100 milliamperes, 200 milliamperes with one of them. I think with the first current sense that we were a couple of videos back, I could get a lot lower than that. I could get as low as 5 milliamperes, although I don't know if I put that on. That was with a higher resistor value. I don't think I put that on video because you put a higher resistor value in your path, it's not going to work for you. I just did it as an experimentation. But anyway, this one shows that for a current in amps, and I'm assuming that A there is in amps, and here's our voltage here, that at zero, well, that's really weird. I'm sorry, at 1 amp, we're going to get, this is at VCC of 5 volts. At 1 amp, we're going to get, is that telling us we're going to get 1 volt? If we cross over there at 1 amp, or is that telling us we're going to get 3 volts? Yeah, well, we're going to have to measure it and see. But what it looks like it's telling us is at 0 amps, we're going to get 2.5 volts out. And then at, we go in at least, and we'll call it the positive direction, the normal direction. Then we go to 2, 3, let's see, 3 amps, and we're going to get right at 3 volts out. 4 amps, we're going to get 3.35 volts. And then at 5 amps, we're going to get 3.5 volts out. So so it's going to be kind of funny. It's not going to be like a times 5 and then you stick, you know, this would be a more complex formula. I mean, not a complex one, you just have to work it out. It's a linear graph, so a linear equation, you can work it out and get what your actual amperage is in if you put this in Arduino or something. But then we can go the other direction and get all the way, let's just go all the way down to -5 amps, and we're going to get just a little above, about what looks like 1.6 volts. Okay, so let's try that, and let's see what, let's see how closely this relates to the graph here. And it looks like all temperatures, if I'm reading that right, all the temperatures have been compensated for, and all the lines are laying on top of each other, so we don't have different lines for different temperatures. Not that that matters here. It's 22 degrees centigrade here where I'm at, so and it's not going to change, so not that that matters here, but out in the field that would matter. With an amp probe or something, and you're out in the field, that's going to mean a lot to you. Okay, let's see what let's see what this does. I just wanted to show you this one other piece. They use a chopper stabilization technique, and we talked about chopper amps before, how they use internal circuitry to offset the voltage offset, the input voltage offset that you get, and gets it down in usually from the millivolts down into the microvolts. And I was looking here to see if they tell. There's a circuit of their patented chopper stabilization technique to take away the input offset voltage, or to nullify it as much as possible. Okay, no, there's some typical circuits of usage. We're just going to look at the V out actually on this. It looks like these circuits, the peak detector, there's one that this configuration increases gain. The one over here increases gain to 610 millivolts per ampere, and so it looks like it looks to me, what I'm seeing is we might not like the millivolts per ampere per unit amps coming out of there. It may be too low, especially to put directly into an Arduino or something. And they don't have what their input offset voltage is. They might have it up top. No, they don't state their input offset voltage, but that's okay. We're just going to play with it as you see there on that circuit. This typical application here. That's the way I'm assuming, based on what I'm looking at, that they have this one based on the number of components and the way it's laid out. They might have an LED on there just to indicate that it's, you know, VCC is hooked up. But that's what we're going to play with and see what comes out of that thing. Let's see what it looks like. Well, I had to go handheld on this one so you could see what I was doing. This is the board, of course, the ACS 712 current sense board, and I'll try not to shake too much. There's the chip. That light there is just a light on the board saying that VCC is hooked up, that power is hooked up is all. Of course, we got our current coming in here and leaving here, and that's through a separate power supply, which I'll show you. And then we have our VCC and our ground coming here, and then our out, which follows this red wire. Our voltage out, which is proportional to our current, comes down here to and is sensed or is picked up by this multimeter. And I'll show you now where the multimeter is. And you remember, right now I've got 0 amps going through this thing. And if you remember, I'll show you where it is true to the chart, where if you have 0 amps, it's about 2.5 volts, I believe it said. And we'll see that in just a second. Let me mount the camera again. Now we have 0 volts going through it. 0 amps going through it. And we've got 2.5 volts, 2.5183 volts. And we saw on that chart, we'll just look at that thing again. We see on that chart where 0 amps going through is 2.5 volts. Well, we're a little over that. We're 25186 volts. But, you know, whatever. That could be, maybe it's temperature or something. I am running a little bit cool in here. Let's see. So 0. So we're going to expect to see this thing go up. I'm going to try to go to 1 amp first. So we'll either see him go to 3 volts out, or, let's see, no, that's 5 amps. We're just going to 1 amp. He's not going to deviate much, actually. Well, let's see what he does at 1 amp. Let's see what happens at 1 amp. What you can see here is that I've got just 1 volt on this constant current, constant voltage supply. I've got 1 volt across there because I have a 1 ohm resistor in series with this the chip that only has 1.2 milliohms internal resistance to it. I don't want to just hook a power supply up to it without some sort of current limit, and I could let the power supply itself current limit, but I don't want to do that. I'll put a 1 ohm resistor in there. We've got 1 volt there, so we should theoretically get 1 amp or thereabouts out of it. And let's see what our voltage then is. We're at 25188 now, and we'll see what our deviation is. In fact, I'm going to write that down. Alright, first let's see if we can get an amperage out of this thing, huh? I've limited to 2 amps, but let me turn it on. Okay, it went to 5.6 amps with 1 volt. let's see. Let me see if I can adjust that up. I don't want to burn up that resistor. I think it's a 2-watt resistor. It's not getting warm yet. We turn the voltage up. Let's see if we can go. Excuse my big fat hand there. There we go. Get us up to 1 amp. There we go. Now we're sitting at 1 amp, a little over 1 amp. And our resistor is not warm yet. Well, actually it is getting a little bit warm, maybe 50 degrees. Well, it'll be good enough for right now. So it's a little over 1 amp. And let's see what our voltage is. I'm just going to swing down. So I turn it off. You know where the BK Precision is by now. And it is 24467. So we've gone down in voltage. So we're going negative. We're going the opposite way that I wanted to go, but that's okay. As long as we get, it just seemed, it makes more sense if it goes up as you increase voltage. But this thing, it does AC current, so it doesn't really matter. So let's do. I'm not smelling any smoke yet, so we're still, although it is getting very hot. Let me write that down real quick. And that's it. Well, a little less than 1 amp. 975 milliamperes. He's 24490. 24490 volts. Okay, I know that's only one data sample, so let's take a look at it. So we got the 0 amps was 25185 volts. 975 milliamperes was 24490 volts. Well, let's take a look at that with the calculator and see what. I'm never going to learn how to go in the right direction with that thing. First time I click it. Let's see. So if we subtract those, 2.5185 minus 2.4490 equals, okay, 69 millivolts per, it's not really an amp, it's almost an, let's call it an amp for right now. Let's just call it an amp. So 69 millivolts per amp. And you know what, I believe that was actually in the data sheet. Was 69 millivolts, 69 millivolts per amp. I believe was in the data sheet. Hang on. There it is. Yes, sir. It's on the maximum side. It's 69 millivolts per amp. That's what you read out of there. That's the sensitivity they're calling it. It can go as low as 63, nominal or typical is 66. And we're seeing 69 millivolts per amp. And we might even say that's 66 since that wasn't a full amp. It was 975 milliamps. So we're looking at the typical over the full range, blah, blah, blah. That's the sensitivity right there. So that is the output, is what you can expect from this. Is we'll just call it what they've got there, the 66 millivolts per amp. So we've confirmed that. We've confirmed that is what they're doing. We did a little bit sloppier than I like, but my resistor was starting to smoke, so I didn't want to cause the smoke alarms to go off, and that could be embarrassing. So we'll call it 66 millivolts per amp that this puts out, which is, that's not very good, really. I mean, well, it's. You can always amplify it. You can always put this in an amplifier, of course. But this is not something you're going to feed directly into the Arduino and read. This is something that you're going to have to put into an amplifier and then go to a computer, into an amplifier, then to a D to A converter, unless you have a built-in one like on Arduino or something. Or if you want more bits, then you'll have to go to a bigger one. More bits on your D to A converter. So that's interesting, 69 millivolts. So we have confirmed that. So that is the Hall effect. So that's probably a consequence of the Hall effect itself. Is that a really good part is that a good thing about it is that you're not interfering with the current that you're measuring, because you're introducing 1.2 milliohms, which is very low, and you're indirectly measuring the current through the magnetic field that it produces. But the downside is that you're 69 or 66 millivolts per amp, and so you're going to have to amplify it and have more complex circuitry on the outside. But that's really not that big a deal. If you want to not interfere with the circuit, with the current itself, that's a pretty big thing. So I would call this a success. So we've measured with a differential amplifier, we've measured with a specific current sense amplifier, and now we've measured with a current with a Hall effect sensor, and we can see the attributes of each one. Very interesting. Thanks for hanging in there with me. I appreciate it. Well, I just had to add something to it, to the current sense. We were getting 66, 69 millivolts per amp, which wasn't really much. It can't be measured very easily. You have to put an amplifier in there. So that's what I did, is I put our old friend, the LTC 1050, the chopper stabilized amp. Since we're measuring low voltage, why not use it? We have it. And I gave it a ×10 gain. So as we can see, we have, it's a very simple amplifier. We have a 10K feedback resistor, 1K coming over from the current sense board. And so we have a ×10 gain, and then I put in a potentiometer here with a 1K going to ground to offset the fact that this thing puts out 2.5 volts. So if you just put 2.5 volts in here, and you have this, and you have the pin 3 of the amplifier, your plus going down to ground, you're going to amplify the 2.5 volts ×10, and so you're going to saturate. Your output's going to try to go to 25 volts. So I put this in here to adjust the pin on the input on pin 3 to give me an output of about 2.5 volts, so that we can swing around that. And so that's what I've done, is I've adjusted this 10K so that we have an output of about 2.5 volts, and then we can swing around that as you go positive and negative around your in your current. So anyway, overall it's a 10K amplifier with a 2.5 volt output to start with 0 amps. And so let's take a look at it, what it does now when we put some amps through it, through our current sense. Well, as we see there, I've got it set up to go no more than an amp, and just 1 volt. This is just my constant current, constant voltage power supply. And our current output, I'll just swing over. Our current output on our circuit is 2.5, blah 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 volts. It's 2.518 something volts. That's the output when there's no current going through it. Current going through the current sensor. So if we put some current through it, let's put 785 mils. Looky there, we jumped to over 3 volts. So that's quite a bit of difference, because we were getting 69 millivolts per ampere, and now we're getting for 780 milliamperes, we're getting over half a volt. Well, what it works out to, I won't pull out the calculator again, but what it works out to is around 69 millivolts per 100 milliamperes, or a tenth of an amp. So it works out to about 10 times, or works out to 10 times more sensitive, or 10 times more gain than what we were getting, which is exactly what we want. That's exactly what we set up the amplifier for. So now you can get, you can read 100 milliamperes and get 69 millivolts off of it, instead of having to read 1 amp. Wait till you get to 1 amp to get 69 millivolts off of it. So I like it. It's a good improvement to it, to the overall circuit, and add some gain to it. And but I just thought you'd want to see what the improvement was, and what the amplifier was, and how if you get one of these Hall effect sensors, how you can add an amplifier to it to add gain. I think SparkFun's already done it. I think they've got one that already adds the amplifier to it, so you don't have to do it yourself. But anyway, it's something it's fun to do if you want to learn how to do it yourself, to put an amplifier in and increase your gain. And I guess that's it. Thanks for listening. I thought I'd add that little bit in there. I did that this morning and put the times 10 gain in there, and I thought you might want to see it. Thank you for watching.